So in this video, we'll introduce the interesting topic about the Taylor series. Taylor series itself is a fairly complicated formula that can be used for any function f of x. But there are a couple of points we need to describe before using the Taylor series. First of all, let me state the formula here. So basically, it's an infinite series, and actually use a summation notation to represent it from n equals 0 to infinity, and for the term x minus c to the power n, which measure basically this term, and for the coefficient, which is the nth derivative of f at the evaluation for the point x equals z, and that's the reason why we have to emphasize that we are looking at a certain point x equals z here, divided by n factorial. So basically, that's the appearance of the series formula, and there are a couple of notes I want to make before doing some examples. The fact is that, to put it in a simple way, first, this one is basically a power series, and it is quite clear that the power series may not be convergent for all x, so you need to find out the points where the power is actually convergent. That's very important. And the second note is about this point x equals c. And basically, because, for example, if you choose a fixed value c, you're getting a power series like this by the Taylor series. Basically, the c actually means the center of convergence for the values of x such that the power series is convergent. So C is like the center. It depends on the value you consider from the beginning for the Taylor series, right? And the next one is that we don't want to talk too much about the deep mathematical analysis, especially maybe it's the first time you see the Taylor series problem. The fact is that such a formula, the left-hand side, the function f of x, is actually the same as the right-hand side by the use of the Taylor series. It may not be correct for all x, as I said, in the first place. We need to check whether it's convergent or not. And in the second place, even if it is convergent, it will not be the same, right? But I'm claiming that they're actually the same for some x at least. And there are lots of bad examples in the sense that maybe it's not convergent at all for all x, or maybe it is convergent. But these two are just not equal. There are some examples about that, but we'll drop it because it's an introduction to the Taylor series. We'll just do a couple of examples in terms of the computation of the Taylor series now. So please look at our first example here. We would like to look at the Taylor series of the function e to the power x, which is a typically standard exponential function at the point x equals 0. This x equals 0 basically means we look at the power series where the center of convergence is 0, right? And let's do the computation. Now we require the point like f of 0. So we can find this point first, which is e to the power 0. Of course, it is 1. And please look at the form of the Taylor series here. We also need the value for the higher derivatives, right? At the point 0 now. For example, I also need f prime of 0. I also need f double prime of 0, etc. For example, f prime of x is actually an easy computation because the function we look at, exponential e of x, never change no matter how many times of derivatives you are taking. So it just never changed, as you can see. So it means our calculation is actually simple here because of the fact that the derivative never changed. So we can just make it look like 1 all the time. Basically, the derivative for the nth derivative at the evaluation for x equals 0 is actually 1 for all n. This is simple because of the fact that the derivative of the function never changed. Of course, if f is changed to other function, we expect that the derivative is not the same, right? And anyway, this fact is good enough for us to write down the Taylor series. So you see the Taylor series is basically the summation of all terms, where the top is the nth derivative at the point x equals 0 divided by n factorial times x to the power n, right? And we know it that all of these are 1 now. So basically, it's the power series 1 over n factorial times x to the power n, right? And that's our Taylor series for the current function here. And by the ratio test we learned in the last couple of videos on the topic of power series, we can actually check that by the ratio test. This power series is actually convergent for all x. And even better than that, actually we understand that for e of x as a function, this one is actually exactly the same as the convergent power series we wrote down in the purple box. They are the same thing. They are the same thing for all x actually, for all x. So it's quite a nice way to understand the exponential function as a power series now, especially now in this case, the formula is always correct. And in the next page, I'll just drop down the well-known formulas that you can easily form by using the Taylor series at the center of convergence x equals 0. So please look at the current page here. We actually have obtained this first formula by the use of Taylor series at the center 0. And similarly, you can actually obtain these two formulas also on your own by the use of the Taylor series. And the fact is that these three formulas behave in the same way in the sense that these are all convergent for all x for the power series on the right hand side. And even stronger than that, we understand that the left hand side and the right hand side are the same for all x. And there's one more function which is also quite famous whenever you apply the Taylor series at the center 0. So I try to write it down here. So please look at my last formula. It is for ln of 1 minus x. And this formula is slightly different in terms of the value of x such that this formula is correct. This one actually has radius of convergence 1. Radius of convergence is 1. And we knew that we apply the Taylor series at the center 0. So basically, it means that on this interval from 0, from minus 1 to 1, the formula must be correct, and the boundary point, of course, you can check it yourself. But I'm just mentioning the fact that the radius of convergence is actually 1, which is not the same as the first three formulas because we understand the radius of convergence must be infinity to cover all the values of x, right? So why am I stating all the four well-known formulas here? Because based on these four formulas, you can easily write down many interesting power series for some other functions. For example, as a quick example, now you can look at the function x cubed times cosine x. And because we knew that cosine x is basically having a very nice power series, as I stated in the top line, you see. So it means the power series for this big function, which is not that easy to obtain if you are insisting on using the Taylor series, because by the Taylor series you have to find all these derivatives, right? And finding all these derivatives, now you see for the first derivative, you need the product rule, which gives you two terms, you see, it's like the product rule. And further, you are expected to use product rule for each term inside f prime for the f double prime, right? So it means in terms of getting derivatives, it's actually not impossible, but we can say it is not inefficient, right? Because it's too time consuming to get all these derivatives done. The easier way is actually by just using the power series of cosine. We understand it's a power series for cosine and it's actually correct for all. We can actually write down the power series of our current function x cubed times cosine x by multiplying the x cubed inside, right? So now the power of x inside becomes 2n plus 3, and the bottom actually is the same, which is 2n, the whole thing factorial. And it's just a simple example to let you know that you can use the four very famous functions and their power series as the building block to obtain a lot more power series representations for various functions which are built up based on the use of them. So before ending this video, just to let you know that because of the fact that cosine x always have this power series as a representation for all x, and our current formula, of course, because of the fact that we only apply the power series of cosine x, so the fact is still the same, that it is true actually for all x. And that's the end of this video.